Okay, I'm going to start. Hi, everyone. I'm going to talk about the Cisco ASA firewalls. So if that's what you're looking for, that's great. That's it. I'm going to talk about reversing, debugging, and automating an analysis on Cisco ASA. So a little bit about us. So I'm working at NCC Group, and I'm part of the Exploit Development Group. And this work has been made with Aaron Adams and myself. So we do vulnerability research, reverse engineering, and exploit development. If you went to this talk hoping to see 0 days and exploit and everything, it's not going to be about exploits. So I'm sorry about that. But it's going to be about tools that help understanding internals and actually help exploiting bugs, which sometimes you have lots of talk about exploits and amazing stuff, but they don't actually show you the tools that you actually built underneath to actually make it happen. So what is a Cisco ASA? Anyone never heard about Cisco ASA? Okay. Anyone heard about Cisco ASA before? Okay. Anyone actually looked at ASA internals? Okay. So you basically analyze ASA from a user perspective or pen test perspective, which is nice. So we're going to talk about internals. But for those that don't know what an ASA is, it's basically the devices you have here. And ASA stands for Adaptive Security Appliance. And it's basically a firewall, a router, a VPN gateway. And most probably you have one in your company network. We have plenty in ours. They are used to establish a VPN and to access the internal network. If you use any connect, that's what you're connecting to an ASA firewall. But internally, it's actually a Linux with a specific ASA folder. And it's different than Cisco iOS because Cisco iOS is actually a proprietary system. Here, it's a Linux base. And it's an Intel architecture underneath, and they support both 32 and 64 bits. And internally, there is one binary that is really important if you look at internals. It's the LINA binary, and it's in the ASA bin LINA hierarchy. And it's basically 50 to 80 meg ELF containing all the ASA features. So that's what you want to analyze, or if you do some reverse engineering, for example. And from an attacker point of view, it's quite a critical device because it's the entry point to the whole network. So basically, if you control the device, you can access VPN information, routing information, access credentials that goes through the router. And basically, it's an entry point for the rest of the network. The small device that is on the top, it's an ASA 5505. And if you want to do some Cisco ASA research, that's the way to start. That's how we started our research. It's a cheap device, and it's good to get started. To give you an overview of what is inside this ASA 5505, so this is a top view where we removed the top, just removing some screws. And basically, you have a CF card, a compact flash card, which basically contains the firmware. So it's a FAT file system containing files, and one of them is the firmware. You have some RAM, so if you want to get more RAM or improve it, you can. It contains several Ethernet ports, obviously, because it's a router firewall. And it also contains a serial port. That's the one that is used when you want to set up your firewall and you don't have any network yet to access it. You basically use the serial ports to connect to the Cisco command line interface and set it up, and then you can continue configuring it later using SSH. But you first need to use a physical access to configure it, obviously. And it's also used if you want to debug it, because you can actually enable a debugger, we're going to talk about that, a GDB debugger, and access it over the serial port. Another thing that we didn't know before doing our research, and there isn't any public research, as far as we know, on debugging virtual environments. But basically, if you are interested in configuring a Cisco network in general, you can use a software called GNS3. So I don't think it's made by Cisco, but it's something that allows you to emulate Cisco iOS devices. But it's also possible to emulate ASA devices, Cisco ASA. So GNS3 supports what they call ASA-V, which is ASA virtualized. And underneath, it's based on QEMU to actually emulate the hardware and everything. But you don't really need to know all that to actually have a debugging environment. We're going to talk about that. So this research has been based on the fact that a few vulnerabilities were released last year, and we wanted to know what was the impact of these vulnerabilities. We do a lot of pen tests, and we have lots of customers that have Cisco ASA firewalls, and we wanted to know, does it have an impact? So we basically looked at the Exodus Intel iKey heap overflow in the Cisco fragmentation payload. So this bug is, in my opinion, quite important in that it's pre-authentication, because iKey is used to establish a VPN to your network. But iKey is the protocol to actually negotiate this VPN. It's pre-authentication. Once you've established your connection, you're not using iKey anymore. But here it's iKey itself, so it's pre-auth. And usually it's available on the internet. So you can, most of the time, you want to access a VPN from the outside. That's what a VPN is used for, right? So they published an exploit for it, which worked for a specific version, but it wasn't like a weaponized exploit. Another interesting vulnerability that was patched as well is the SNMP Stack Overflow in the way they parse the object ID. This one was released as part of the Shadow Broker leak in August of last year, and because it targets SNMP, most of the time SNMP is used internally, and also it's post-authentication, meaning you need to know the shared secret, which is the community string for SNMP, to actually be able to use it. But what is interesting is it's a Stack Overflow, so it's been here for many years. It targets a lot of devices. The last and final interesting aspect is that for most of these bugs, it's easier to exploit if you actually know the versions of the ASA beforehand. And to do that, we figured out that you can actually use other bugs like WebVPN leak, where you basically talk HTTPS, or HTTP, you talk HTTP, which is encrypted with SSL and HTTPS, and you target the HTTP protocol, and you find a way to leak the versions in that the server will return an error indicating the ASA version. And using that, you can combine bugs and exploit, for example, the iKey overflow. So what did we do from that? So we wanted to weaponize exploit and figure out how it's easy or not, this kind of thing. And we basically had a constraint, which is Cisco ASA versions, you have 200 different versions. So how do you deal with that? So we started our research by using like GDB and existing tools, and it started to be really annoying for us. So we had to build some tools to help us doing this. And also we wanted to analyze internals. So what we did is we basically built a tool called ASA Firmware, which helped us to analyze firmwares in general, to unpack and repack them. And we also needed that for debugging, because sometimes there is no debugger GDB in the firmware, or you want to analyze, you want to enable certain features, or maybe disable ASLR to its debugging. So we needed a way to unpack, repack firmware. The second thing we needed is a way to deal with different firmware, because we have 200 firmware, and if you want to analyze mitigations or things in different firmware, or even retrieving symbols, you need a way to automate that. Otherwise, it's going to be a really painful job. And I wouldn't be here today. And then, obviously, we need to debug it and see the differences between different versions. So that's the role of ASA DBG. So this presentation is going to be about presenting you these three tools and what were the challenges. And these three tools allowed us to basically build weaponizable exploit for almost 200 versions on different architectures and for different versions of the protocol. Okay, let's go. So let's talk about the first thing, which is analyzing the firmware. So the firmware, you can either get it from the CF card, which I told you earlier, but if you want to get different firmware for different versions, you can actually do it. If you have a Cisco account, you can download them from the Cisco websites. If not, you can actually find most of them on Google, because you have lots of people that need access to their Cisco ASA firmware at some point, and so they share them on their public websites. But anyway, if you find one firmware on the internet, I advise you to check the MD5 against the Cisco websites, just in case. Otherwise, you may install a backdoored firmware. So the way they named their firmware is ASA, then the versions.bin, basically. And so, for example, you have ASA 924.bin, and you have ASA 924 SMP.bin. So SMP is for multiprocessing, but actually, we figured out that usually, most of the time, it's a 64-bit. So if you have SMP, you're pretty sure it's going to be 64-bit. And then you have ASA 961 SMP versus ASA v961.qco. And in this case, the first one is 64-bit, like we said, and the ASA v is for virtualized. So the second one is to load in GNS3. And it has a different extension. So the first thing we tried is basically to analyze the firmware. If you do some embedded analysis of embedded devices, I'm pretty sure you know binwalk, because it's the Swiss Army knife for analyzing raw files where you don't know what's going on inside. And it's been developed by DevTTYS0. And basically, you just say binwalk -e to extract, and then the firmware, and it will basically list you what is inside and extract it. So in this case, we can see that it has a gzip, and then it has 2 gzip files. And if you look at the actual files, it actually contains, so binwalk is clever because it knows it's a gzip, so it will just extract it for us. And you get an ELF and a CPU archive. And in the case of the CPU archive, it also renamed it to rootfs.img because it found the name into the listing above in blue, rootfs.img. So the ELF is actually the Linux kernel, and the rootfs is actually the file system. So we're interested in looking at the file system. So we use a CPIO tool to actually deal with unpacking the rootfs. And using that, we figured out that indeed it's a Linux system, and it contains a specific ASA folder. So we can check that the ASA bin liner is ELF 32-bit in this case. So it confirms what I said earlier, Linux plus ASA folder and Intel architecture. So now we have a way to unpack, okay? But it would be nice to be able to repack, because in some case, we're going to need that. And if we look at it further at the actual format, we can figure out that there is a rootfs, and then, the rootfs, because you can figure out the gzip magic and the rootfs.img string. And then you have a little after you have the Linux kernel, which has a specific string direct booting from and a gzip magic as well. And then at the very end, you have the Linux kernel command line, which is a long string that is passed to the kernel to indicate lots of arguments. And before this Linux kernel command line, you have two integers, which basically correspond to the kernel size and the rootfs size. So it's not documented, but you can figure that out just because binwalk gave you the file, so you can figure where the size of the actual gzip, and then just figure out where it's stored somewhere, and then figure out, oh, that's the two next to each other. I'm pretty sure it's the size, and then you can just test modifying them and see what happens. So for example, here we can unpack the rootfs, modify files, repack it, and as long as the rootfs that we've repacked is shorter than the actual rootfs, we can re-inject it, patch the size, and it's going to work. So you're going to say, okay, but how do you inject new files? Well, actually, you can delete other files that are not used. So actually, it works. You can just, without knowing the whole format, you can modify it, and it's going to be accepted by the actual device. So we have a way to unpack and repack firmware. That's what we wanted. For the QCO format, actually, we were like, okay, we're going to have to do something similar, but QCO is actually a well-known format used by QEMU. It's basically a way to have different partitions, and QEMU will handle these different partitions. And so because GNS3 is based on QEMU, you can use standard QCO tools. So you basically connect QCO to a specific device, and then you can mount partitions. So in this case, the first partitions, we can see that it contains several files, like the grub, and it also contains an ASA.bin. So then we can come back to what we already knew, and everything applies. So we are able to unpack and repack because we can mount the thing. So this is how we built ASA firmware. We basically we have different modules. The first one is the QCO module, which will basically allow us to mount the partitions to unpack it. We access the bin. The bin module will handle the bin format and will allow us to unpack the rootfs. And then from the rootfs, we can use CPIO to access LINA. Once we have LINA, which is the main Cisco ASA binary, we can patch it, optionally modifying the actual features. And then we can re-inject it into the rootfs. We can modify some files, like modifying some scripts or disabling ASLR or stuff like that. So for example, we can enable GDB at boot, inject the GDB server if there isn't any, disable ASLR, just what I said. And then we basically, the rootfs, we re-inject it into the bin format, and if it's a QCO, we can re-inject it into the QCO. And the device accepts our modified binary, so we know we can do anything we want, basically. The last thing we are interested in is we want to mine, we want to do some data mining, because we are handling 200 firmware, and all have their different specificities. We want to know which one has ASLR enabled, which one has certain things. So we can basically, extract all the firmware, and then just have a way to analyze all them at one time and extract information. I'm just going to detail that. But before detailing all the data mining, I'm just going to explain the way the boot works. It's interesting because it allows you to understand how to enable GDB at boot. So and also we've used that for our debugging. When the Cisco ASA boots, you have the first piece of software that's going to run is called Halbronn. And if you attach like a screen, if you attach to the serial and just look at the actual logs on the serial line, you'll see the Halbronn name, and you can see that there is a prompt that you can interact with. And the Halbronn, by default, it will basically load the ASA.bin on the file system, on the CF card, and that contains the Linux kernel and the root file system that we just detailed. But the root file system contains not only LINA, but among other files, it also contains the LINA monitor file. And basically, the Halbronn will load the Linux kernel, and the Linux kernel will load like the regular init and all the processes, but it will end up loading LINA monitor. And LINA monitor will actually load LINA. That's the way it works. And the thing is, if you reverse engineer LINA monitor, you'll figure out that it accepts specific flags, like -L, -G to say debug, and -S to provide the serial ports, -D to get more debugging stuff. And it's loaded, LINA monitor is loaded using a specific script, and you can basically modify the script to provide these flags and actually enable debugging at boot. So this is something Exodus Intel found out. So thanks to them for providing this. So the way it works is LINA monitor attach GDB server to LINA. Okay. So we with all the firmware we've unpacked, we wanted to do some data mining to understand, okay, there are 200 versions. Are they all the same in terms of mitigations? We know Microsoft is doing amazing things. Windows 10 is like a lot better than Windows 95. Is there anything similar on Cisco ASA? And the response is actually yes. So I'm not going to list the 200 versions because it's going to be boring, but I just took like a few versions just to give you an idea. So, for example, in this case, if you look at the 924, you have ASA 924 and ASA 924 SMP, and both are the 924 version, but there is 132 and 164-bit. And if you take the 932-200, you can see that there is the 64 SMP and there is a 64 virtualized. So I'm trying to list them all so we get an idea. Right. And the 802 is actually the oldest kind of version, and the 981 is actually the most recent kind of. So the first thing we can do is we can look at the actual ASLR, if it's enabled or not, just looking at the VA randomized ASA flag set for the kernel, for the Linux kernel. And we can actually quickly see that they enabled the ASLR at some point after 9.5. And what is interesting as well is that they actually enabled the position-independent executable, the PIE, in Line I itself, meaning they did it well. They enable ASLR both on the Linux kernel part and on the binary, which you're supposed to do that. So you actually have ASLR enabled for your binary. What is interesting as well is they didn't enable NX on the same way. So the way they did it is you can see below 932, they didn't have ASLR and they didn't have NX, but they actually enabled NX on the 943 and 944 branches, but they didn't enable it on the 9.5, but instead they had enabled ASLR on this one. And then on the 962, they actually had enabled both of them. And what is interesting is, I'm going to talk about that later, but the 962 branch and the 9.5 branch live at the same time, meaning they actually, I mean, it's an assumption, but it looks like they tried different mitigation on different branches at the same time. So they don't have any stack canary. So if you find a stack overflow like the SNMP one, it's an easy win. You can return on the stack. And if you don't have depth, you have your shellcode like in the 90s. They don't have any full railroad, so you can overwrite pointers on the global offset table. And they didn't have any symbols, but at some point in the 9.5 branch, symbols started to appear. So actually you can, if you load a lineup binary, you have all the symbols, like 200,000 functions, because it's quite huge binary with all the symbols. So we notified Cisco about that, and they actually removed the symbols in the latest version. In terms of Linux kernel, we can see that they used Linux 2.6, and they moved to Linux 3.10 at some point, corresponding glibc. And in terms of heap, because the IKE bug is a heap overflow, it's important to understand the heap internals because it influences how hard it can be or how easy it can be to exploit the bug. So we can see that they used to use dlmalloc 2.6, then they moved to dlmalloc 2.8.3, and then to ptmalloc 2. So we had to reverse engineer the binaries, obviously, to figure that out. And what is interesting about that is that the old dlmalloc that they use doesn't have any heap safe linking, so you can abuse the heap. And they also use like a mempool structure, which is inline on the heap, in addition to the actual dlmalloc one, which is specific to Cisco, and they didn't have any safe unlinking either. And what's interesting is on the newest versions, they actually have safe unlinking on the heap, but they don't have safe unlinking on the mempool, the Cisco part. So you can still abuse the heap. potentially. So I already talked about branches already, but I'm just going to give you more information. So in this case, this table is in the advisory of the IKE buffer overflow I talked about earlier already. And you can see that they list all the branches. And for example, above 8.7, you have a patch. So if you are on the 9.0 branch, you have to be 9.0.4.3.8 or later to be patched. Meaning if you are 9.0.2 something, you're not patched. But then some branches don't have any patch, so you need to migrate to another branch. And what is interesting here is if you take two branches, the 9.1 and the 9.2, if you take the 9.1.7.4, because it's later than 9.1.6.11, it's patched. But if you take the 9.2.2.4, because it's before 9.2.4.5, it's not patched. So if you forget the table, but just look at the line, 9.1.7.4 is patched, but 9.2.2.4 isn't, it's a little bit weird. And actually, if you look at the actual release, it makes sense, because the 9.1.7.4, even though it's a 9.1 and the other one's a 9.2, it's 2 years difference between the two. So actually, it's easy once you know, but it can be confusing if you don't know. The other thing that is worth talking about is what version is end of life. There is no, as far as we know, there is no public summary of which ASA branch is end of life. But actually, using this advisory I've just showed you, you can actually deduce the branches that are end of life. And you end up having something like that, which shows you that versions below 9.0, they are all end of life. So if a new bug arrives, you're screwed. And for the versions above 9.4, you're okay. Or above 9.1, you're okay, except 9.3. I honestly don't know why 9.3. Maybe they have like a long-term branch, I guess, long-term branches, and some branches that they don't support for a long time. Okay, so we want to reverse line now. Exodus Intel published a trick to actually rename functions. So that's something very frequent when you reverse engineer embedded devices. You have lots of debugging strings. And in this case, you have the IKE v2 log exit path logging function that is called by many functions. And the function that is calling the logging function, the name is passed to the logging function. So in this case, IKE v2 parse config payload is calling the logging function. So we know that the function that is calling IKE v2 log exit path is IKE v2 parse config payload. So we can script things to rename a bunch of functions. So that's very nice. But actually, because we actually found out that quite late, that the recent versions now have the symbols. You can actually take one binary that has symbols and just use binlif to get like all the juicy bits to all the firmware. Okay, so I showed you like a history of different ASA versions. We know we can unpack, repack firmware, but we want to debug what's going on. So we built an ASA debugger, ASA DBG. So before showing you why we built ASA DBG, I'm just going to show you how painful it was for me before I built this tool, before we built this tool. So I explained to you that when you boot the device, you have the output on the serial. And you have the boot ROM, and you can hit a key to actually interrupt the boot. So in this case, it's break or escape. But I did a mistake. I hit space. So instead, it's going to boot the one by default. And this is me. This is me because I don't hit the right key. So I'll do it again. This time, I hit the right key. And then I have a text file with all the commands to actually copy-paste the commands. So I get this prompt from Halbronn, and I can specify I want to boot this firmware with this config file. So here, yeah, the boot takes a little bit of time. So it's going to basically give me, in this case, a root shell, where I can patch the script to actually enable GDB at boot. So I copy-pasted the command to modify this script to modify line monitor command line. I'm modifying this, and then I'm starting init just to continue booting the device. So I'm just skipping this part because it takes 2 minutes to boot. But at the end, you get a GDB server waiting for you to connect. So in this case, you can just exit screen and just connect with GDB on the serial line. So you connect to it. You specify the files that you extracted from the firmware. So GDB knows what file it's debugging. And then you use target remote the device to actually connect to the serial line. So in this case, I didn't use the right command. I actually failed on my demo, so I just kept it. And then you manage to connect, so you get your GDB attached to the GDB server on the device. So in this case, for the sake of the demo, I'm just setting a breakpoint into an IKEY function so I can trigger my breakpoints. I'm continuing execution. So I'm skipping, it takes a little bit of time to boot, so I'm skipping it. And basically, I'm just pinging the device until I get a response, meaning it's up and running. So here I'm just using one script to send some IKEY messages so I can trigger my breakpoints, just to show you it works. And here, because there is no symbol, when I look at the backtrace, I cannot use it easily, right? So it's quite painful to actually know what's going on. So I'm hitting continue. And then I get a signal that is triggered. And it's because Lina has a watchdog mechanism that will prevent debugging. If you debug for too long time, it will trigger a signal. So here, you're screwed. You need to start booting the thing from scratch. So I just skipped it for you, because otherwise you're going to be all sleeping. Digestion is already here, so I don't want to kill you. So I started again. I enabled the watchdog, and this time I'm having real breakpoints, and it's working fine. But the other problem is, it would be nice to do Control-C. So if you use the GDB already, you know you can Control-C and access GDB, but in this case, you cannot. It's not possible. So it's your GDB, if you do Control-C twice, it breaks GDB. And then you have to reboot the device, 2 minutes again. I think you get the idea. So that was me again. Right. So that's why we created ASA DBG. So what do? We didn't reinvent the wheel. We reuse lots of existing tools, like GDB itself, but we tried to automate things so we could actually analyze lots of firmware and in a better way. So the first thing we assume is that GDB server is enabled. So instead of using the old technique that Exodus Intel gave, we can instead enable GDB directly by modifying the file and repacking the firmware. So we get this GDB server waiting for us. So here is in GNS3. We can see GDB server is waiting for us to connect. So we assume that. So the other problem I just demonstrated is that GDB will trigger a signal, Lina will trigger a signal if you don't disable this watchdog mechanism. So thanks to Exodus Intel, we can disable this watchdog, which is clock interval symbol. So the last thing is, as I showed you, it's not possible to Control-C. And we actually realized that it's not possible to Control-C only on real devices, like real hardware, both 32 and 64 bits. And it didn't pose this problem on the emulation one. So we assume it's due to the fact that the Control-C character that is sent on the serial line is badly encoded, or there is some kind of problem on the serial line with this Control-C special character. So the thing we ended up doing, which is quite hacky, but actually was really, really helpful, is we actually patch Lina to support like a debug shell, so we could have a way to interact with Lina. So the way it works is we have Lina with our patch code. We attach ASA-DBG to GDB server, and GDB server will be attached to Lina. And basically what we want is to trigger our patch code to get a debug shell. So the way it works is we have GDB, and we have our listening netcat on the host, and we connect over SSH to Lina, okay, using the regular SSH function. But because we patched code in the SSH handling function, it will basically connect back to our netcat. And so we get actually a Linux shell. And it's different if you already analyze a Cisco device, you get a Cisco shell. It's not the same shell. The Cisco shell, you input Cisco commands. Here it's a Linux shell. We're underneath. And the reason we want that is because we can list the processes. So we can, for example, access the proc maps. But at first, we did it really to actually interact with Lina, because we can list the Lina PID, and we can actually send a SIG trap signal to this PID, and then get a GDB back. So it's a complete hack. I completely agree, but it saved my life. Well, maybe not, but it helped me. So here we have a better debugging to be a little bit finally useful. We want symbols. GDB doesn't have symbols, especially on most of the firmware. We used existing tools called RedSync. And basically the idea is you can synchronize a debugger and IDA Pro. And if you have this kind of need, even for other things that are not related to Cisco, like WinDBG to IDA, and you keep copy-pasting stuff, I really advise you to try RedSync, because it's a really nice tool. But basically, we modified it to add specific things, but it works with many debugger, like XCC4DBG, GDB, whatever. But we used it for GDB. And the way it works is you have a plugin in IDA and a plugin in GDB, and they interact with each other with a simple protocol, and they synchronize. So in our case, we have GDB server running on the ASA, our ASA-DBG based on GDB on the Linux host, and then we have IDA that can be on the same host or on a different host, and they are all synchronized. So how does it work? So let's say you have GDB. Well, actually, you have where you are in IDA, and you can actually step in, and in IDA, you will see where it goes. And you have the graph view, first advantage. You have a way to modify your function names, so you can actually add comments, things like that in IDA. And also, by default, you have a backtrace that doesn't have any symbols. But because we have this synchronization, we implemented a new command, which is beautiful backtrace, BBT, which basically is going to fetch the symbols and just display it for us, so we can enjoy, finally, our debugging. So we analyzed a heap vulnerability, and at that time, there wasn't any tool to analyze heap internals. So we built 3 libraries that we already presented at B-Sides, so I'm not going to talk about it. If you were interested, you can have a look at the B-Sides talk slides, and there is a video, I think. But basically, because the ASA had different heaps, we built different tools to analyze these different heaps. So to summarize the ASA-DBG architecture, we use ASA-DBG specifying a name of the target we want to debug. And we have a config file which, for this specific target, it's going to list the version, the architecture, where we extracted the root file system, and the firmware and config file that we want to use. This config and firmware needs to be on the ASA itself, but we can, using ASA firmware, we can build all the firmware and just drop them on the CF card, and then just choose which one we want to debug. So the way it works is the ASA-DBG will look at the config file, retrieve all the arguments, all the parameters, and then we have an external database that contains specific symbols for each target. So for example, clock interval is the watchdog that we need to have to actually debug a target. Mempool array is a symbol that we use for our libs to find where things are in memory to analyze the heaps. So the database, we can build it because we can automate retrieving things for the different firmware. I'm just going to talk about that just after. So our ASA DBG will connect on the serial port. So we have a layer of abstraction which we call COM, which will allow you to either connect on the serial line for real devices or on the telnet port for GNS3, for QEMU. It will basically interrupt the boot, look at the files, boot the specific files, and then once you get the GDB prompt, you have a GDB init which is like a template, and we can patch the timeout, the watchdog, load the libraries and things like that. So all this is integrated in ACDBG. You don't have to do that manually. It will load the libraries we need, and it supports continuing automatically loading additional GDB scripts if you want to analyze specific things, and synchronize with IDA using RedSync. So this video is going to be a lot shorter, but basically you start ASADBG, it's going to listen on the serial line. So it fetched the config to know the config file name and everything. It will detect automatically at boot that the boot ROM is waiting for us to input something. It's going to input the boot, the asa.bin and the config file. It's going to detect when the root shell is happening, and it will automatically input the commands to patch the script, load GDB. So in this case, it still takes 2 or 3 minutes to boot, but at least you can do something else in between, and you don't have to worry about it. So it will detect that GDB server is waiting, start a GDB, connect to it, and then you can load additional things, or you can automatically continue if you want. So the other thing we were interested in, because we're dealing with 200 versions, and because now we have a way to choose which one we want to load at boot, we were interested to know how reliable we could, how we could make the exploit reliable for different versions, and was it even possible? So the way it works is we can load a given firmware, we can detect when it has finished booting, fire an exploit, then detect the results by scripting above ASADBG. For example, if it's a remote connection bug, you can check if you get a reverse shell back. If it's leaking the version, you can check if you actually leaked the version. You can save that in a database, and then either it worked, so you issue a reboot command, a reload command on the SSH port, or on the SSH port, or if it crashed, you listen on the serial port anyway, so you know it, you figure out it crashed, and you just wait for it to reboot, and so on. So what we did is we have our IKE exploits working for different versions. We test them all. We can figure out which one works, which one doesn't, why, then fix things, and figure out that at the end, even if you have it working for different versions, most of the time we figured out that the reliability is around 50% due to heap inconsistencies, because you need to do some feng shui, and remote bugs are hard to make reliable, a little bit like eternal blue, if you're familiar with all this kind of bug. And then for the SNMP bug, because it's a Stack Overflow, we actually are able to fix problems and have a 100% reliability. For the web VPN leak, there is no reliability going on here. It's either you leak the version or you don't leak the version, but we're interested to know which one was actually vulnerable to which leak, because basically, based on the Cisco advisory, it wasn't really clear for us to understand which one was vulnerable or not. And here, because we have a way to automate things, we can figure out which one is really vulnerable and which one is patched. So I'm almost done. But basically, if you followed my presentation, we were able to patch the firmware, patch Lina inside the firmware, or repack the firmware, and we were able to load the modified firmware. And so it doesn't look like there is any secure boot. There isn't on the device we tested, with the versions we tested. But in GNS3, we actually get something interesting, because when you try to boot the modified image, you actually have this error saying the digital signature of the booted image file did not verify successfully. And if you actually look for this string on the files, on the file system, it's actually in Lina monitor, and because Lina monitor loads Lina. And so you reverse engineer that. We did that, and we actually figured out that there is a check, obviously, because it doesn't load. And what we tried is just to patch the jump to the code calling this error, to just jump to loading Lina, and actually it worked. So there isn't any secure boot going on. So we were able to do our research on GNS3 as well. So the last tool I'm going to present is IDA Hunt. So the problem we had is we wanted to analyze almost 200 Lina binaries. And each of them is almost between 25 and 85 megs, depending on the version. The latest are like bigger than the previous one because there is more features. So that's me when trying to load an 85 meg in IDA. I don't know if you tried already. It takes a while. So if you have 200 files to load, you have time to go to take a coffee or go to a security conference. Hoping you're not here because of that. But anyway, IDA Hunt, the way it works is it's going to use IDA and automate analyzing binaries using IDA. So it's really simple tool that's not really clever. But the way it works is it spawns different instances of IDA in the background. It doesn't show any GUI, and it allows us to script things. It's not specific to ASA firewalls, but we applied it to Cisco ASA. But if you have like Patch Tuesdays that you want to analyze, script things in IDA, create IDBs for different files, different samples, malwares you want to analyze, embedded devices, UEFI, modules, or whatever, as long as IDA knows the formats, you can use IDA Hunt. So the way it works is you use IDA Hunt from the command line. You specify the folder that you want to analyze. It's going to analyze all the files from this folder, except that you can specify a filter that will indicate which files you want to analyze. So in our case, we specify that we only want to analyze the Lina files, for example. And then you can specify --analyze to analyze that, to indicate that you want to do the initial analysis in IDA, which is the first thing that happens when you load the binary in IDA. And then you can use a script argument, which will basically allow you to pass scripts, IDA Python scripts to IDA. So they're going to be run in IDA. So you can script things. And in our case, we were interested to hunt for symbols, basically, like the watchdog symbol. So we can use that to retrieve the watchdog for 200 firmware. So the way it works is you start IDA Hunt. It lists all the files from this hierarchy. It first checks which file it needs to analyze. Then it's going to load the analyze module to do the initial analysis. And the way it works is we'll spawn IDA-q.exe, which is the IDA executable in the background. So it doesn't show anything, but it just waits for the different processes to finish. So you can customize how many instances of IDA you want to load. By default, we chose 10, because otherwise the fan will just, but 10 is good with this kind of laptop. And then you can specify the scripts that's going to be run as well in IDA. So it allows us to automate retrieving symbols, like the clock interval for debugging, symbols for analyzing heaps, and for the debug shell that allowed us to control C to get symbols. So the first one, AAA, admin authenticated, the function we want to patch Liner to have this reverse shell. And the SOX process server start is a function that you need to enable to actually enable this reverse shell communication. But we actually used it as well to retrieve all the symbols we needed to weaponize the exploits. So in conclusion, I talked about 3 tools. So one to deal with ASA firmware, one to deal with debugging in ASA, and the third one to hunt for symbols in IDA, which is not specific to ASA, but we use for ASA. So these tools have just been released, so you can access this link. We use these tools really to understand internals, so we have a better knowledge of the tools, of the internals, but also to debug exploits. So if you're interested in this kind of thing, you can use our tools. Right, that's all I have to say. Thanks for attending.